Okay, let's do the bulldozer one here. It says a bulldozer of mass capital M. I'm actually going to label that on here because it's not labeled on the diagram. So the bulldozer's got a mass of capital M, pushes a cube of cement of mass lowercase m, even though that's enormous, across rough ground. That is an indicator that there is friction. The bulldozer and the cube are speeding up. In other words, they are under acceleration. If you are accelerating, then that must mean that you have a net force on you that does not add up to be 0. So we know that our horizontal forces cannot be balanced in this case. Our vertical forces may be, because this thing isn't accelerating up or down, so those can balance, but since we're speeding up, we have to have a net force horizontally. So let's start to draw the free body diagrams that they're going to ask for here. So on this one right here, let's start with just the forces on the bulldozer. Now they never explicitly said it. Normally they actually will. They'll say something like capital M is greater than lowercase m. And they didn't say it here, but they say it later in the problem. So I'm going to go ahead and say I'm working with that assumption right here. So what are the forces on the bulldozer here? Well, we know we got the force of gravity. And I just drew it 6 down. There's no way to yet indicate what that should be. They didn't give us any numbers. So let's call that the force of gravity on the bulldozer there. And then we do know that however long we drew it down, we got to draw the same back up. So 1, 2, 3, 4, 5, 6. I'll call that the normal force on the bulldozer there. The bulldozer's speeding up, so there has to be a force to the right on it. And so assuming it's going not in reverse, but it couldn't accelerate the block if it went in reverse, the block would just be set there. So it's going this way. So there's got to be some force here, and it's the friction on the ground. It's like we were talking about in class there. The friction on the ground pushes this thing forward. So again, we don't know how much. It didn't give us any numbers to work with. I'm just going to draw it 5. 1, 2, 3, 4, 5. No reason whatsoever. And I'm going to call this the force of friction on the bulldozer. There. So a little italicized F with a little B there. Now, you may not realize this one at first, but we know later when we go to do the cube that the bulldozer pushes to the right on the cube. And therefore, according to Newton's third law, bulldozer pushes right on cube, cube pushes left on bulldozer. So let me draw that one. 1, 2, 3. Now, again, how many I draw back is arbitrary. I'm going to call this the force by the cube on the bulldozer there. But here's the one thing I do know. Since it's accelerating to the right, then I know the net force has to be to the right. And therefore, this friction force that the ground exerts on the treads has to be greater than the force the cube pushes back. Has to, because the net force has to be to the right to give us an acceleration to the right. So now let's do the forces on the cube. I'm going to work with what it says here, that the big mass is greater than the little mass. Again, they didn't say that before, so maybe you drew them the same or one bigger. 1, 2, 3. I'm just going to draw this 3 down. I'm going to call this the force of gravity on the cube. In the same, 1, 2, 3, up. So I'm going to call this the normal force on the cube. Then we mentioned over here, the bulldozer is what's responsible for pushing this forward. And I drew it 3 blocks over here, so I got to draw it 3 blocks over here. So 1, 2, 3. And again, I'm going to call this the force on the cube from the bulldozer. Now, friction finally comes in on the block. They say it's a rough surface. So as the block is scraping past the ground, friction is going to be pushing back the other way there. So I'm going to draw friction up here. I'm just going to draw it 2 cubes long, and I'm going to call it friction on the cube. Now, how do I know to draw this 2 versus 3? Well, to some degree that's arbitrary, but I know that the force of the cube on the cube from the bulldozer has to be greater than the force of friction on the cube. Why? Once again, because it's accelerating this way. So if it's accelerating that way, then the net force has to be that way, and so this force has to be bigger than that one. Lastly, let's do it on the entire system here. So now this has to be taller. It really should be these two added together. So I drew this one as 6 up and this one is 3 up. So this one should really be 9 up would be the normal. I guess technically I should start with the force of gravity on the system would be 9 down. This weight plus that weight. This would be the normal force on the system, would have to balance out the force of gravity on the system. And then what are the sideways forces on the system? We know we have to have some. The system as a whole is accelerating. The one thing we won't count is this force of the cube on the bulldozer and vice versa, of the bulldozer on the cube, because that's an internal force. It won't matter for the acceleration of the system. So I've got this force of friction on the bulldozer from the treads, and I drew that 5 long. 1, 2, 3, 4, 5. So force of friction on the bulldozer. And then I've got the force of friction on the cube back, and I drew that one as 2 long, like that. So now that I've got my diagrams, let me think about each of these in the equations. Again, they want you to do the F equals ma for each one of these. So what are the forces in this case? We've got the force of friction on the bulldozer, that's the tread friction there, to the right. And then I got minus backwards the force from the cube on the bulldozer. So those two forces are the net horizontal force on the bulldozer, and that's got to be the mass of the bulldozer, which they just call capital M times acceleration. What about for the block? Well, let's look at the horizontal forces on the block. We got the force on the cube from the bulldozer forward. We got the force of friction on the cube backwards. The mass is just called little m generically, just like it is here, and that's times the acceleration. And so then over here on the third diagram for the system, what do we have? We have the force of the friction on the bulldozer pushing us forward. We've got the force of friction on the cube going back the other way. The mass is the mass of the system, which will be big M plus little m times the acceleration there. The last thing they want you to do is to use some numbers to actually solve a problem. They tell you at the bottom of the page there that the mass of the bulldozer is 1,000 kilograms. They tell you that the mass of the cube is 500 kilograms. They tell you that the force of friction on the bulldozer from the ground is 5,000 newtons, and that the force of friction on the cube is 2,000 newtons. So now let's set it up here to solve. Let's use this equation right here and just start to plug in. So the force right here of friction on the bulldozer is 5,000 newtons. Back the other way, we have to subtract out the force of friction on the cube, which is 2,000 newtons. That's got to equal this entire mass right here, big M plus little m. So we're talking about 1,000 plus 500, so 1,500 kilograms altogether, and that is times the acceleration. So from this side, 5,000 minus 2,000 will be 3,000 newtons is equal to 1,500 kilograms times A. Divide that down, and you can see the A equals 2 meters per second squared. Technically, we solve for the acceleration of the system, but this is also the acceleration of the cube and also the acceleration of the bulldozer. So you could work backwards, for example, to find the force of the cube from the bulldozer there and solve it for that. So there's a challenge that you guys can try right now.